Hello, my name is Mino. I'm Professor Emeritus of the University of Tokyo, and the title of today's talk is Biological Wastewater Treatment as a Technological System. As I said, I started my research career by looking at enhanced biological phosphate removal. I'm an engineer, but I was interested in rather basic scientific aspect of EBPL, and my major concern was biochemical or microecological mechanism of EBPL. Then I changed my research direction a little bit to more engineering side, and the topic was modeling of activated sludge process, and I was a member of IAA task group on biological wastewater treatment, and the outcome of this task group was IAA activated sludge models ASM number 1, 2, and 3. Further later on, I completely changed my research direction to more soft side. Sustainability is the most important keyword at that time, and I was looking at not only the technical side, but also social side of sustainability. And I was founding coordinator of graduate program in sustainability science, GPSS, at the University of Tokyo. So today's my talk will be based on this experience of mine. So I will start with very basic aspect of EBPL as an example of the research, and then I will further go to a very comprehensive, very holistic aspect of biological wastewater treatment. So the first thing that I would like to tell you is my how to say, very impressive or striking experience, which I call Acinetobacter story. I will tell you later, I will explain you later why I call this in that way. So as I said, my first research topic was biological phosphate removal, and this is very interesting technology because just an introduction of an anaerobic zone at the front end of usual traditional activated sludge process of the aeration tank of activated sludge process promote enhanced biological removal. Why? Because by the introduction of this anaerobic zone, phosphate accumulating organisms, which must be responsible for EBPL, will be accumulated, will grow in the process. So from the research point of view, the key question was who, when, and why, means who must be this phosphate accumulating organisms and why they develop in the process. The primary, the initial answer to this question is Acinetobacter. So at that time, that was in 1980s, many microbiologists actually interested in the process, EBPL, because it is quite a unique process. It's very interesting. Then they applied culture-based method to identify who. And Acinetobacter was found to occupy a major portion, 60 to 90% of bacterial populations in the activated sludge process with high phosphate removal efficiency. But later on, we found that this was not the case. This was not correct. Accumulobacter or more diverse microbial communities must be responsible for EBPL, and it was shown based on molecular methods, means the methods to look at DNA sequences, By applying this method, we realized that Acinetobacter was no more the primary species responsible for EBPL, but Acinetobacter, this is another species, and other diverse species contributed to EBPL. How we understand these two facts, or the two two observations. If you look at this whole bacterial community, only a very small part of the community can be isolated and grown on agar plate. So at the initial stage, we were counting only the portion which could grow on this agar plate. So this is, I don't know, maybe 1% or maybe less than 1% of the whole community. Only within that small portion, Acinetobacter was found to be the number one. So Acinetobacter was number one among the bacterial community that developed on the agar plate, but never the major population in the entire bacterial community. But later on, by analyzing DNA sequences, you can identify more comprehensive bacterial populations. But still, we should keep in mind that all technologies, all technical methods must have their own bias. So even we are looking at a quite big portion of the whole community by using molecular method, but still that's a part of the whole community. That must be something we have to keep in mind. So what are the lessons learned from this story, Acinetobacter story? You should not look at only what you are interested in, but you should try to understand which parts or which components or which aspects of the entire system you are observing by the method you are applying. So you should not look at only a part of the whole elephant, and that is something that all engineers must consider when you do their job. Not only engineers, maybe. So based on this understanding that the holistic view or comprehensive view is very important, I would like to try to explain various characteristics of biological wastewater treatment. I have listed 4 here. The first one, biological wastewater treatment, or actually the wastewater treatment system, is a part of primary urban infrastructure. There are many infrastructures in urban system, and BWT is one of them. That's why many physical, economic, and social constraints existed in design and operation that should come from the constraint to the urban infrastructure. There are a lot of constraints. The second one, this biological wastewater treatment or the wastewater treatment is a very important, essential part of for our life, for our comfortable life. But it is located at the downstream of urban system. That means they are less visible, they are annoying, and they are producing little valuable matters. Actually, we should not think in this way, but many people, they're just typically many people think this way. That means our system, the wastewater treatment system, is something invisible, and so people do not want to pay a lot of money to that. This can happen. We cannot accept, from the social point of view, we cannot accept very expensive system in wastewater treatment system. The third point, biological wastewater treatment is an open ecosystem. This is actually very scientific characteristic, but related to many issues. They are exposed to severe environmental selective pressures, and this facilitates very serious biological competitions within the system. That means if you apply a certain environmental conditions, then the best fit populations may grow in the system, and others were competed out. The fourth point, you are engineers, and you have to work with the wastewater treatment plant. What you receive is the wastewater, and the wastewater characteristic like quality, quantity are not controllable. What you are coming in, that's something that you have to accept. However, when you optimize the system, there are very limited controllable parameters because we cannot apply very expensive system. So all these four characteristics are related with each other, and you can think about some more. But definitely these very comprehensive and holistic aspects, different aspects, various aspects of DWT may influence your job. Okay, now I will come to more specific issues. What frames or views can you apply to BWT when you work with BWT or when you design, operate, or manage the system? I have listed 5 frames here, so I will go through one by one. Okay, historical view. That means if you look at how technologies related to water pollution control have been developed, then you may realize what's the incentive or driving force of the development. For example, at the beginning, we were suffering from waterborne diseases like cholera, and we had to remove those pathogens from our life. So what we should do was the development of sewer system to throw away the wastewater, or actually your excreta. And once you develop this piping system to discharge the wastewater, then of course the receiving water body may be polluted because of the pollutants you are discharging. So what we need was we had to construct the terminal wastewater treatment plant at the end of the pipe. However, if you just stick to the end of pipe type of technology, then you cannot really deal with various pollutants. Like if you have a wastewater coming from the industry and some heavy metal are contained, these are something that cannot be removed in usual treatment plants. So you have to add some more technologies, but they are very expensive. What's the cheapest? What's the more cleaner technology? That is the separation at the source of wastewater. So there are many different ways of coping with this, but optimizing the system should require various thinking, comprehensive thinking. And later on, we should not limit all this discussion into the sewer system or wastewater system itself, but our life must be somehow changed to improve our environment. So that's this stage. And if you look to this history, then what we can learn from here is if you try to solve one problem in front of you, then the solution may create the next problem. And then if you try to solve that problem, and the solution may create next. So anyway, we have to have very comprehensive and holistic view, not only the system that you are looking at, but the systems which surrounds the system that you are looking at. The next point, I assume that many of you are engineers, and the material balance or material flow analysis is a very powerful tool to understand your system. So let's do it for biological wastewater treatment. First, the primary target of our treatment is organic matter, organic carbon. So carbon balance here. The carbon in the influent or organic matter in the influent may be partly oxidized. They are converted to CO2 and just released to the air. But major part will go to the waste sludge because what we are doing in the system, in the wastewater treatment system, is you just let the microorganisms grow in the system. So the organic matter in the influent may be converted to the cells of the microorganisms. Is this treatment? What I mean is you are not really treating the wastewater, or you are not removing the wastewater, the organic matter in the wastewater, but you are converting the organic matter in the influent to the biomass in the waste sludge. So only by this wastewater treatment, it's not complete. What to do with this waste sludge? That's the thing that you have to consider. By applying this material flow analysis, you should realize that. As for nitrogen and phosphate balance, you very easily realize that not all nitrogen or phosphate in the influent can be removed from the wastewater. In case of typical domestic wastewater combined with the typical activated sludge process. That's the reason that we need to add some additional way of nitrogen removal and phosphate removal. How about heavy metal? In case of nitrogen and phosphate, it is possible to add additional technology treatment system to remove nitrogen or phosphate. However, in case of heavy metal, once it's mixed with the wastewater and coming into the wastewater treatment plant, it is very difficult to really remove. However, what I mean is, if you look at the effluent quality, the heavy metal concentration is nearly zero. Where do they go? They are accumulated in waste sludge. So putting heavy metals into the wastewater actually mean that you are accumulating heavy metal in the waste sludge. So the toxicity of the waste sludge is really the problem, and it makes the situation more difficult to handle. This aspect may lead to the next point, that is, are you looking at the removal of only organic matter, nitrogen, and phosphate in biological wastewater treatment? One thing that I have to emphasize here is this first point. Wastewaters is a reflection of human life. So materials excreted from human body and the materials that is used in our life can be transported in domestic wastewater and are converted to wastewater treatment plant. Why I'm saying this is important? Because in order to treat organic matter, it is of course good or necessary to accumulate and converge the all organic matter into one place. But how about others? Like we may have heavy metals. Actually, we don't want to have heavy metals in our wastewater. But for example, in the natural environment, there must be some heavy metals existing naturally. Or, for example, in the roof, in the outer wall, you may use different heavy metals like zinc, copper, and so on. So they are somehow through different ways, different pathway, they come to the wastewater treatment plant. They are accumulated, they are converged to one place. This could create the problem. Antibiotics, endocrine disruptor, these are basically spread in the environment, but you are accumulating them. So you have to be really careful, not only the material that you are interested in, like organic matter, nitrogen, and phosphate, but there are unknown materials, many unknown materials in the wastewater, and that must be somehow considered in certain way. Radioactivity. When we means the Japanese people had the Fukushima nuclear plant accident, unfortunately, there were big spreads of radioactivity in the natural environment. And immediately after the accident, what I considered was, these radioactive substances may be accumulated finally in the sludge. So the sludge handling should be a big problem. And actually, it was really a big problem. And what I mean here, I want to say here is not only the substance that looks important at a certain point is, of course, your responsibility. But there are many other substances, materials that may be hidden behind, and sometimes it may emerge because of several reasons. Pathogenic microorganisms and viruses, these are the same. For example, gastroenteritis causing viruses like noro, adeno, or rotaviruses. If you detect these viruses in the wastewater, that shows the risk of the contamination of, for example, human excreta. COVID-19, when we had COVID-19, the monitoring of COVID-19 viruses in the wastewater gave you certain information. Means it's a very good indication of future potential outbreak of COVID-19 in the near future. So a sign is already shown in the wastewater, in the sewer system. The last point which I gave here is any useful materials in the wastewater. I'm not talking about this aspect too much. You can think about the possibility of recovery of many useful material, or you can consider the different way of usage of wastewater for different purposes because of the material contained in the system, in the wastewater. So it's up to you. What do wastewaters carry other than physical matters? We have been looking at material substances in the wastewater, but what else? Of course, energy. We use gravity to transport the wastewater, and that means there must be some potential energy. Why don't you use them? The heat. Typically, the wastewater or domestic wastewater has a little higher temperature compared to the atmosphere during the winter time, especially countries like Japan. In the summertime, vice versa. So this temperature difference can be used as heat energy if you have a good heat transfer system. Information, as I said, as I already explained, the example of COVID-19 viruses or some microbiological indicators. These information are very important to evaluate the risk of something. So depending on what parameter you are measuring, the information is very interesting aspect of the wastewater. What else? Please think. At the end, I'd like to summarize the relation between BWT and society. Of course, biological wastewater treatment or wastewater treatment system is a part of urban function. So some functions necessarily in urban system it can be materialized by using wastewater treatment system. For example, the wastewater can be regarded as the water resource. So the reuse of wastewater is one thing. The wastewater treatment system occupy a big space. So why don't you use this space for other purposes like recreation park? Not only recreation park, there are many other functions of urban system, and that can be replaced by wastewater system. So the wastewater treatment plant or the system can be integrated into other urban infrastructure. The second point, the relation between BWT and emergency evacuation. This aspect is very important, particularly for Japanese people. We have a high risk of having earthquakes. Actually, we had many earthquakes in recent years. So the space of wastewater treatment plant can be regarded as evacuation space, or we can store food there. That would help this evacuation activity. The biological wastewater facilities are already an emergency toilet by itself. If you just open a manhole, then it's toilet. And the wastewater, it's dirty water, but it can be emergency fire protection water. You can split the wastewater to extinct the fire. Finally, I would like to indicate the relation between the biological wastewater treatment and the modern technologies. We have AI, we have nanotech, material sciences, and biotech, and so on. If you think of the combination of these technologies with the wastewater treatment, biological wastewater treatment, then you may come up with many ideas. I will not touch on the details in this part. Probably you may know better, and please think this aspect also. So I have been talking about how we can develop holistic and comprehensive way of thinking when we work with biological wastewater treatment. And along with this line, these are my final messages. Do not stay in the traditional field of wastewater treatment technologies, but look out for possible various interfaces with other social functions. The second, intentional changes of flames through which you can watch wastewater treatment facilities may bring you new insights that might give you fantastic ideas for future innovations. And be flexible in thinking and brave enough for changes. I think that's all for today, and thank you very much for listening.